Okay, so you are privileged, I would rather say, to have one of the pioneers of GNSS-based atmospheric probing in India, Dr. Nirvikar Dashora, as your speaker today. He's a very, very busy person, but because of our long relationship and he was associated with all the previous programs, ATAL FDPs, and he has been kind enough to agree to deliver this lecture. So Dr. Nirvikar Dashora is presently working as scientist SF at National Atmospheric Research Laboratory, NARL, Kadanki, Andhra Pradesh, under Department of Space, the Government of India. He joined NARL in year 2007 after his PhD. His PhD work has been one of the first from India on study on ionospheric TEC and scintillation using GPS observations. So you can very well understand why I was eager to have him as one of the experts, because I know many of the participants here, they are also researchers in the very same field, and many of the young student, they have asked me questions or they're interacting from this point of view. So he has been the first from India to publish the GPS, TEC and scintillation study in the year 2005. He is MSc in physics and MTech in space and atmospheric sciences. At NARL, he has been developing a ground network of GPS receivers for high-resolution remote sensing and imaging of the atmosphere. His main research interests are space weather effects and ionospheric variability over equatorial and low latitudes. He has published more than 40 papers. I think the number would, it was an old CV from where I copied. It would be more than 45, I think, or maybe 50 papers in peer-reviewed international journals, and presented more than, once again, it should be more than 55 papers at various national, international conferences. With the advent of Indian NavIC system, of which you are hearing every day, he aims to develop scientific applications of this uniquely configured constellation along with GPS GNSS using ground and satellite-based experiments. He has been convening a series of workshops on GNSS NavIC applications, and he has delivered more than 35 invited lectures on this subject at various workshop symposia. Just 1 month ago, I had the opportunity of hearing him on one-day workshop on NavIC at IIT Indore during the UTSI RCRS conference. So with that, I invite Dr. Dashora to deliver his lecture, and I'd also request the participants to type in your questions whenever you will feel at the end of the lecture. You can directly ask the questions. So grab and properly utilize this opportunity. So Dr. Dashora, the screen is yours.
At the outset, I wish to thank my very dear friend and a very great colleague, Professor Anindya Bose, for inviting me for this lecture. And he has been actually doing a lot of effort in popularizing and actually educating a lot of masses around West Bengal and all over India. And kudos to for his effort. And with this, I also thank him for the introduction and his good words about me to the participants. Coming to the today's talk, I would share my screen and then I will start talking. Just it will take 1 minute. Can you see this?
Yes, now it is visible.
Okay. So just 1 minute. I will stop my video for saving the bandwidth. And I will present again. Yeah. So I would like to talk more about the atmospheric research using the signal from GNSS and NavIC. However, I will also touch upon some of the atmospheric measurements that we can perform for the neutral atmosphere and the lower atmosphere, like water vapor and other measurements like soil moisture and all. But then the major portion of my talk will be on ionospheric research. Uh, you can note my email ID, ndashora@narl.go.in, or my Gmail ID, which is my full name. And you can always, even after the talk or any time in your career, if you have any queries regarding what I am going to present today, or otherwise, you may please put a email to me, and I would be happy to respond to you anytime. So to introduce you to the subject of what you call the ionosphere or atmospheric effect, um, I have lined up some of these slides in this outline, but then not withstanding the outline, I would try to go here and there a little bit just to have interaction with you, and maybe try to understand how much you are with me, and then we will move forward. Because I think we are going to have at least two and a half session up to 9 o'clock in next 2 hours. So let us be with together and then try to understand what this all about. To start with, I am right now at NARL, this location which is provided by the GPS map, and GPS or GNSS or any other constellation which is used for satellite kind of navigation provides us the position. So these are the positions used from the satellite, and then we can pinpoint our location from the from using the GPS on a map. So this is the utility of what we are going to touch. But then not only this utility, we are going to touch something else beyond what position and timing provided by satellites. NARL is a autonomous ordination at present under ISRO, and Professor Dr. A.K. Amit Kumar Patra is the present director of NARL, and we have a vision of developing the atmospheric forecast models through observations and instrumentations. And we do actually lower atmosphere, middle atmosphere, and ionospheric research. You can say in one word that above the surface of the earth, we have almost all kind of measurements up to the top of the ionosphere. And also we try to understand from satellite measurements beyond the ionosphere into the magnetosphere and towards the sun. So in NARL campus, we have something like 70 or more host of suite of instruments, and they compose of one of the main instrument, which is called the Indian MST radar. Now it is active phased array MST radar. It was established in 1993 as National MST radar facility, and now it has been upgraded, and several other capacities have been enhanced. We also have LIDAR, which is called the Rayleigh LIDAR. We have one DigiSonde. We have one climate observatory network tower for aerosol trace gas measurement. We have cloud and convective systems group with X-band cloud radar, and one dedicated radar with scanning east-west capacity called the Gadanki interferometer radar, which is installed in campus itself. It is the Giri radar. Further, we have these GPS receivers and network that I will touch upon. So to begin with, for the uninitiated, if you have been listening to some of the previous talks, you might have come to some understanding that the radio signals which are transmitted from satellites actually travel through the space, which is not vacuum. For your information, it is kind of a medium which has several different kind of densities, and the composition changes throughout. So a radio signal is composed of electric and magnetic field perturbations which travel in space in transverse mode. And this all started way back in something like 60s, when American and other nations started using the radio signals from satellites for purpose of transmitting communication, and even for the purpose of navigation. So initially they used the Doppler effect, and the satellite system was known as transit system. It was developed by Navy, and mostly it was used for the seaborne or the ocean-borne ships and the other systems around the globe. And uh, they had this kind of two frequency transmission, 145 and 400 megahertz. That was in kind of VHF band, and partly in above VHF band. So this kind of transmission could not sustain due to several technical and other maintenance issues. So simultaneously, if you see the historical perspective, USA and Russia both started developing a global satellite-based navigation system. So USA developed the global positioning system and Russia developed the GLONASS. However, as we know, in 1991, with the disintegration of USSR, there was a kind of a break in operation with or minimization in operations with for 1 decade. However, GPS was fully operational by 1995, and you can see here that the refurbishment and modernization of GLONASS was also done, and from 2008 onwards they have a complete constellation of 24 satellites which are transmitting in dual frequency mode. And during last decade, as per the plan and the requirement of the users, Americans have managed 31 satellites in space segment, and further updates can be seen from the gps.gov, which is a governmental website for from the America, United States of America. There have been several details about this. No need to go into detail. We have 31 satellites, and beyond what we know about satellite constellation, we humans think about several different things. So the curiosity-driven questions and queries have grown us into what we use as number of applications, and these applications have come from not only GPS but a gamut of GNSS system. They are known as Global Navigation Satellite Systems. We already know GPS and GLONASS, but then Galileo has been put up in space by European Union. Is a large effort. There are like more than 30 satellites, and BIDU is a kind of a very big effort by Chinese people, and they have put more than around 35 satellites. Earlier it used to be called Compass, but then now it is BIDU. Official name is BIDU, with multi-frequency transmissions and multiple satellites of different kind. Like they have geostationary satellite, they have kind of geosynchronous satellite, and other different kind of satellites. So uh, we also have in India called Gagan and IRNSS, which is now called NavIC. So just to introduce you what are the differences from the global systems to NavIC system, or the Indian system which is developed by ISRO. I have put for this table. So the Gagan are the two satellite, and Gagan is basically the SBAS, a satellite-based augmentation system. They use the GPS signal and transmit the corrections. However, NavIC is the independent satellite navigation system for particular region. So Indian region. So they have in that system we have 7 satellites. In IRNSS, the altitude is 36,000 kilometers against the other constellations, and we transmit L5 and S-band signal. It was like the constellation in space was first from the 2015. You can have more number of information, much more information from the ICD of the NavIC. I will share with you little later. And this is how the constellation look like. If you see far from Earth, a kind of a view of the constellations and their orbits, and you see now what I was talking about, how BIDU looks like different from point of view of the different class of MEO satellite, geo satellite, and GSO satellite, geosynchronous orbit satellite also. So they have developed a system which is also robust and comparable to GPS, GLONASS, and Galileo. Coming to the regional navigation systems, at present there are two, one by India and other by Japan. Indian system is known as IRNSS, or what we call NavIC now, Navigation by Indian Constellation NavIC, and it has 7 satellites. There are further plans for upgradation, but at the moment these 7 satellites are located at 34 degree, 55 degree, 83 degree, and 115 and 131 degree. These two pair of satellite at 55 and 111 degree, 11.5 degree, they are into the kind of geosynchronous orbit, and the other three are in the geostationary orbit. And if we see from ground, the ground path comes to be like this from the equator. If we are somewhere in the over the equator, then the ground path of the NavIC or IRNSS satellite comes to be in blue color, and I is for Indian, and 04 is the number of satellite, 0304, so up to I01 to 07. Whereas if you see the QZSS system, it is having a few satellite like 3 or 4, and they are in Molniya kind of orbit with kind of elliptical orbits, and they provide the this regional navigation solutions for Japanese region. Um, Coming to NavIC, which is the navigation by Indian constellation, there are two different transmissions as carrier frequencies, L5 signal and L signal. L5 signal is transmitted with central frequency of 1176.45 megahertz, whereas S-band signal is in 2492.028 megahertz, means that it is around 2.4 gigahertz, and L5 band is 1.1 gigahertz. More information, which is like what you can say detailed information about the whole NavIC system, its uses, applications, and the official information is put in interface control document by ISRO, which is available on the website of ISRO in this particular address. So ultimately, we will come back to our original question, that how it works. And actually, the large part of my lecture is also related to how it works and how it performs. So one must know, before we know further into the ionosphere or atmospheric part of it, that how GPS works. And I hope in past few days, you might have come to know how GPS works. So GPS actually uses two carrier signal, L1 and L2, at 1.5 gigahertz or 1.2 gigahertz. It has a CDMA kind of code division multiple access bi-phase shift key kind of modulation, and then each PRN is transmitting one unique pseudo-random code, which is called the PRN code on each of the signal. So in L1 signal, we have three different codes, and L2 signal, we have always P code in the GPS. But the different constellations can have different combinations of these codes which are transmitted, or these modulations which are transmitted over different signal. For example, NavIC will have both the course acquisition code and the precise code and the navigation message, both in L5 and S-band. So either of these band can be used by the civil or the military applications. This is how GPS actually work. GPS is actually a system, if you really see, with space segment, control segment, and user segment. You might have known about these all, so I will skip. Other than telling you that the orbital velocity is very fast, means it is around 3.8 kilometer per second for GPS satellites, and the period with which the satellites move is around 12 hours. So they appear around twice a day for a given place. If you put a receiver continuously operational, you will see every satellite passing over that place with varying elevation and azimuth 2 times. This is the control segment through which the Americans control the whole segment. It works a 24-hour cycle with the transmissions with the control segment in L band, and then ultimately is like master control station, and then several this thing. A navigation message, you might have heard already, is composed of Keplerian parameters for each orbit, and assuming that there is a satellite at particular time t, then the satellite positions are actually estimated and transmitted from the ground antenna to the satellite in advance, and then this in turn, whatever satellite is having information over orbit is transmitted to user. So what we actually receive is a satellite orbit which is estimated in advance or broadcasted. What people say, it is a broadcast orbit parameter, and then from that broadcast orbit parameter, we actually estimate our position or the time. So these Keplerian parameters are very important from point of view of whatever application we want to do. Um, Ultimately, the user segment is composed of the receivers, and we use in different environment different types of receivers. So the basic requirement why they have done is for the position and time, and of course for the defense purpose. But then now GPS or GNSS become a commercial entity, and with a large business volume over the entire globe. So one must learn how GPS works, and actually it works in terms of time of arrival, which somebody can give a kind of a triangulation method. You might have heard of it. Triangulation method depends upon the transit time of the signal from satellite to the receiver. You multiply transit time to the speed of the light, and you get the distance or the range, direct range, line of sight range from this. And if you know the range in this term, like assume that you have transmitted one signal and it comes here, then what we know is that we know the um, uh, satellite position, and then what we have here is the range which is coming from the cross correlation of the code. So each receiver will have one code which is the or the modulation which is transmitted from satellite. Already it is existing in the receiver. When the when the receiver receives the transmitted signal, it try to cross correlate whatever is already existing in the receiver. From that cross correlation, since these are very unique codes, they only cross correlate with them. They mathematically it is not possible to cross correlate any other, because with length of the code is very large, around 7 days for the CBA code. So what we get from the cross correlation is the time delay, the estimated time delay from receiver, that is called the plus t or small t. That small t we get from the cross correlation of the basic modulated code, and with that the first range estimation happens. This time difference, which is what transmitted versus the receiver replica, when we multiply with velocity of light, and if we only are receiving from one satellite, then what we know is that if the user position is here, then satellite A has one distance d1. We get one distance d1, this distance d1, and then in that case our reference frame becomes the satellite. So from satellite we are at d1 distance, but we don't know we are anywhere on this sphere of the d1 of the d1 radius. So what we do, we actually increase one more satellite. So we receive another signal from another satellite, which is B satellite. Then what we have simultaneously, we are receiving from A and B. Then we have mathematical equation which is equivalent to like two spheres are kind of intersecting with each other. So we have one volume coming up with one two basic line equations. Then if we include one more, with this is what is called triangulation, then we get one single point of um, uh, in the 3D space, and these distances d1, d2, d3 are estimated from three different satellites. So this is like a pictorial presentation of if we have more multiple satellites, then how we can get user position. This is triangulation, and ultimately this is how it works. So three different equation with unknown parameter of x, y, z from three different satellite, and if we have fourth satellite, we can get x, y, z, and t also. So this is a linear system of equations that works, and then we get it. Also, there is a issue with which direction all four satellites should be. So I will tell you later which is the best. This is called the dilution of precision. Is a separate topic altogether, but if time allows me, I will come into that. So what happens is that this is how we start. That what is the distance measurement and whether there are any errors. So there are errors because of the ionospheric and tropospheric delay, which is the maximum if you compare with other errors. You see here 5 to 45 and 2 to 6 meter, and this happens because there is a refractive medium through which the GPS satellite signal or GNSS or NavIC or any satellite signal passes through this, and then there are multiple refractions happening. So the multiple refractions means more delay. Delay means from the expected time which we consider to be vacuum, what time delay happens due to the electron density or the other neutral density is called the signal delay. That's why it is called delay. So it is signal delayed against the vacuum. So this delay happens, uh, and nobody knows how much delay is happening. So the most of the computations are done. All the computations are done using the vacuum, considering or assuming this is vacuum. But then the signal is transmitted with ionospheric and tropospheric delay models. So one can correct those delay, but then models are inaccurate. So we will go into depth of this subject, but then we need to know what is ionosphere. So ionosphere is simply put forward is this pictorial presentation for any beginner. There is a day which is receiving sunlight and radiation from the sun from different kind of like you can say the X-ray, extreme ultraviolet and ultraviolet, mostly UV and soft X-ray produce different layers through the production. Once you have the ions and electron, free ion and free electron, then due to the chemistry and due to the dynamics and the electrodynamics, formation of layers happen. And very interestingly, we get 4 different layers. Layers means is a continuous, there's nothing like segmentation. This is a continuous electron density profile. However, there are peak. So the peak is happening at D layer, E layer, F1 layer, and F2 layer. For historical reasons, we call them in this name. However, when you see at the same time Earth is rotating, so there is always a large or half part of the ionosphere is night. So in the night, what happens is that you don't have solar radiation coming continuously. So what you have is leftover ionization, which still remains freely moving with the scale height of what you call the Debye length, and this can be called still ionized layer. So the layer which is above 250 km still remains in the nighttime, which is called the F layer in the nighttime. So the F region, which is most important for the purpose of our communication, actually is the peak density of the ionosphere happens in the F layer. So which is around the 200 to 600 km, but peaking around this thing. This particular sun, I have put sun spots just to indicate for people that this is the sun spots actually appear in different numbers, and then they change. So there is a solar cycle. So when we have this radiation coming from sun, there is also a solar cycle, and the sunspots actually indicate the solar cycle, but they do not tell directly what is the radiation and the level of the radiation. So we measure the radiation from sun in different wavelength from different satellite and ground based measurement, and then we see the effect of that radiation changes in the ionosphere. Actually, Earth ionosphere is looking like this. If you see the vertical profile, this is the temperature profile and this is the number profile. So when we see the electron density, it starts from somewhere from around 100 km here, and during daytime, as I have told you, it is growing up to almost like 6 into 10 power kind of 10 power 6 centimeter per cube number density, and in night time it simply decreases. However, above around 250 km, you can see then night very small difference. Further, this spread in this is actually indicating the solar cycle, solar activity spread, the maximum for the maximum solar activity, minimum for the minimum solar activity. When we come to the temperature profile, you can see that this is the temperature in the troposphere. It decreases with height, then again it increases in the stratosphere, then again it decreases and reaches to a minimum point above around 90 to 100 km in mesopause. And then since the gases actually diffuse freely above 100 km, so the individual gases will have individual profiles of temperature, and an average thermospheric profile for the electron and ion temperature can be put in this case up to 1000 Kelvin. So the temperature grows and grows and grows in the ionosphere up to 1000 km and above. This is how it looks like. What ionosphere is composed of, you can see ionosphere composition actually is derived from the neutral composition. Since we have a lot of oxygen and nitrogen in our composition, as we know, the ionization density also is maximum contributed from the O plus ionization. You can see throughout, from the bottom of the profile to the top of the ionosphere, from about 150 kilometer to the 1000 kilometer, O plus ion density actually peaks and dominates the total production of the ionization. At the lower levels, other composition like NO plus and O2 plus heavier ions actually dominate the electron and ion density profile. And this is the day and night type curve for the different solar conditions. So it is not easy to understand the ionosphere and its electrodynamics, owing to owing to several kind of complex effects, which are actually can be considered from like a sandwich region between lower atmosphere and the sun. Ionosphere is actually an interface for human or for the living being or whoever lives on earth towards the open space. So it is a sandwich region. So from lower atmosphere also we have several kind of gravity wave, tides and turbulence and different kind of forcing, which again comes from the solar activity. Then we have heating, then we have the photoionization in upper atmosphere, then there is a formation of the ionosphere, and then this day and night composition happens. Then once it becomes plasma or the electron and ion, then it has to follow the magnetic field line, because of the properties of the plasma. So the geometric field becomes very dominant when it becomes the ionized plasma, and it actually plays very important role in producing major phenomena which is known as equatorial electrojet and the anomalies and the nighttime phenomena like equatorial plasma bubbles. These different kind of phenomena actually are of little more concern for the latitude like India, because we are in a low latitude or equatorial latitude for the geometric point of view. So we actually receive in ionosphere, Indian ionosphere, these phenomena with much more strength and much more variability. So we need to understand all these things. Is a complex phenomena, but not going into detail. I want to show a pictorial view. This is how it looks like during daytime. Assume that you are 4 o'clock IST, Indian Standard Time, and the variations which are in the TEC or the ionosphere, representative variations in the ionosphere, actually are for the production. There are loss processes, and then there is a transport. Ultimately, what we receive here is like the maximization of the ionization away from the equator. That is called the equatorial ionization anomaly in the both side of the equator. And this dark line is the geometric or deep equator. 0 degree deep is there for the geometric declination angle, and then these plus minus 20 or 30 degree latitudes are known as equatorial and low latitude from point of view of geometry. So these two large perturbations, actually if you compare all around the globe, are the highest electron density regions. These regions show the large variability, large amplitude perturbations. They actually are changing very drastically when the solar storms are happening, and they are also changing from day to day, seasons and all. Several kind of changes are happening. So these changes actually affect the signal and the what we call the access path delay. That is what I started with. So this ionosphere is not a very quiet medium. It is a very turbulent and highly variable medium. So the delay changes. Once the delay changes, your error changes. Once the error changes, your position, you don't know whether it is correct or not. So ultimately, this is how the ionosphere and the NavIC or the GNSS signal are connected. If you want to read more about ionosphere, actually it is a very classical subject, and there are quite a good textbooks available. From the scratch, if you want to know, then there is a good book by Burdwan, Radio Waves in Ionosphere, with the complete treatise for the mathematical treatise for the Appleton-Harty formula, and then how actually the refractive index of the ionosphere comes in, this n. And uh, this is where actually the Nobel Prize in ionosphere was given to Appleton in 1947. It is important to understand that ionosphere has been a subject of intense investigations from 50s, 60s, and 70s and 80s. And later on, when GPS and other satellite navigations become important for the modern society, again ionosphere has become very, very important because it produces different kind of variability. So we need to know how actually ionosphere and GPS signal is connected. So as I told you that the refractive index of the ionosphere, which is we can write as small n, actually is a very complex quantity. So this can be simplified using several assumptions. Those assumptions we can follow through Radcliffe, the magnetoionic theory, and through the Kenneth Davis very nice book of ionospheric radio. And we get this n in terms of NP, or the phase refractive index, 1 minus x upon 2, where x is composed of the E square, n is the electron density, m is mass of electron, epsilon naught, and then omega. Omega is nothing but the plasma frequency by divided by radio frequency, is a angular frequency which is composing the x factor. This x actually finally decides the changes in the refractive index of the medium at any given altitude at given time. So you see this n, which is the electron density, actually is governing the refractive index. Now if the refractive index changes, then we need to understand how it changes and how our signal is connected. So what we do, we do a Taylor series expansion, we get NP in the terms, and this becomes a complete constant. If we take this constant, this becomes 40.3 upon f square in multiplied by n, and 1 is 1, so 1 minus 43. This is phase refractive index, which is connected with the group. Group means the modulation. So I told you that every signal of GPS has one carrier frequency. You can consider that as a kind of a phase of the signal in terms of when it is affected by the index of refraction. And the group, which is the modulation, like C by A code or P code, they are affected by this kind of refractive index. So ionosphere has two kinds of refractive index variations. One are the phase refractive and the group delay. So here you see that one is like with comparable to the vacuum. So 1 minus this, and this is 1 plus. So one is some factor is subtracted from the with respect to the vacuum, or and one factor is added to the with respect to it. How it turns out to the velocity connection. So what is velocity? Velocity is nothing but the ratio of c upon refractive index. So I mean the refractive index is nothing but the velocity of the signals ratio. So from there we get the velocity, phase velocity of the GPS signal or any other radio wave signal. So from here we actually get the velocity of the phase and velocity of the group. From here we get the total delay. So now, as I told you, that the delta t that we measure multiplied by c becomes the geometric delay. But since this delay is not simple, it depends on the velocity. So then what we get is that phase delay. If there was c only multiplied by dt, but then there is a vp, so there is a difference. So this is called the delta phi, or how much phase is changing. So finally, when you get delta phi, it comes to be negative, means that phase delay is negative, means that phase is advancing. Phase is advancing by how much amount? So 40.3 divided by f square. F again is nothing but radio frequency. So like you put here L1 frequency 1.5 gigahertz, and then here is the ndl. N is, again I told you, here is the n is nothing but the electron density, and then dl is nothing but the integration between satellite to receiver. So this whole quantity of electron density integration becomes the TEC. Now the TEC plays a role in advancing the phase. However, it becomes a positive signal here, so TEC becomes plays a role in group delay. This is how we tell the whole integral part as TEC, and then we express that delta phi into ionospheric delta phi in terms of 40.3 TEC upon f square with negative sign, which is called the phase delay in terms of TEC. And when we call TEC from group delay, it becomes like this 40.3 TEC upon f square. And this is how TEC, I have just for the pictorial view, like if you integrate from bottom to top, all the electrons for the one particular column, which is 1 meter square cross section, we get the TEC. So what I told you in previous slide is explained here in little more detail. Now this detail we connect with the radio refractive index. Radio refractive index has this kind of connection 1 plus n, where n is the refractivity. Refractivity has two components. One is the ionospheric component, and one is the neutral atmospheric component. So when we write the L1 band delay, which is called the modal equation for the GPS, we write this is true geometric delay, which is assuming that there is a signal only traveling with the speed of light. Then there is a clock delay, T delay, and all. But you see here, ionospheric delay and tropospheric delay. These are the delay which are composed of the atmospheric delays. They are part of your pseudo range estimation. The pseudo range which I have shown you earlier. So this is how they are connected, and the physics of it and the mechanism of it are connected. Now, here if you see, the yellow color parts are the frequency dependent and the pink color parts are the frequency independent. So this gives us a kind of a hold on ionospheric delay, that if we take difference of the observed range between P L1 and PL2, P or C by A code, L1 and L2, difference of delays, then these all delays will cancel out. And what we get is like kind of ionospheric TC with some kind of noise and the other code biases. We can actually estimate ionospheric TC if we have dual band frequency measurement. That is what is the reason, original fundamental reason behind the always two frequency transmission from any satellite navigation system, that we can get rid of ionospheric delay. Coming to these two delays into further detail, the tropospheric delay actually is made up of the dry gases and water vapor, and L1 and L2 are the microwave band. So in this band, actually dipole component of water vapor actually becomes very dominant for reflectivity, and what we can get from this tropospheric delay is two parts, dry and water vapor. In ionospheric delay, it is frequency dependent, and if we estimate the differential delay, we get the ionospheric delay. I hope you are understanding. So when we want to understand the zenith weight delay from GPS, what we call the water vapor estimation using GPS, if some of you are interested, you can follow this particular slide. That the zenith weight delay here, if you see here, this one. So you need to actually first remove the frequency dependent parts, which are in yellow in color. Then you need to precisely remove the orbital error or extra orbital difference between these two frequencies. Then you need to remove the clock errors, and then we already know what is the exact distance from the satellite, precise satellite orbits which are transmitted later on to the precise receiver location. So you must understand that for water vapor, the location of receiver must be very well established, and then location of satellite in the orbit must also be very precise, first of all, so that you get this direct range very accurate. Then you must correct for all different delays. So once you correct all different delays, actually what is remaining delay is actually the tropospheric delay. That is what I have written here, that one has to remove all other delays to get the water vapor content delay. And actually it is composed of the dry air and water vapor. So hydrostatic delay and wet delay, and you can compose of different models of the zenith wet delay and the zenith hydrostatic delay. The difference of that becomes the zenith wet delay. Zenith wet delay, if we multiply with the mean temperature of the atmosphere, which is composed of the K, then it becomes the precipitable water vapor. And precipitable water vapor is what we actually refer as the water vapor using GPS. It is called the integrated water vapor. Again, it is not a profile. It is single value of integrated water vapor throughout the atmospheric column. Coming to the TEC, as I already told you, TEC is the integral of satellite to receiver electron density. And when the configuration of satellite is a slant with some angle with respect to your receiver horizon, then this is the ionosphere, and signal passes through several layers of ionosphere. So what we assume that there is a single layer of ionosphere. This is the assumption only. However, there will be error because of this assumption, one must understand. But we actually assume and we try to see that there is a point in ionosphere at 350 kilometer which is cutting the ionosphere. But there is no such point because ionosphere is continuous medium. But then for purpose of simplifying the mathematical conversions, we do that. And what we do is we get one yellow color slant delay, and here we convert in vertical direction is called the vertical delay. So vertical delay is what actually is most important for for the correction purpose when they transmit the corrections. All the transmissions are happening in vertical delay term. So this is from the observation how we get vertical delay. However, the vertical delay which is transmitted needs again to be converted into slant delay. That is another issue. Why it is another issue? Because we already assumed the ionospheric single layer assumption. Anyway, there are good models which are actually assuming now double layer or multiple layer assumptions, and in NavIC we have used the dual layer mathematical combination of ionospheric layers, and it is performing better than other models. We know
Uh,
these
uh,
applications.
just a moment. So as per our plan, you can take 10 minutes break now. So it
Okay.
is 19:52, and we will once again join around 8 o'clock. So
Okay.
you
So
can
this
have
is my
some.
last slide for this
Okay, okay,
session.
okay, okay. No
We
problem.
can
Please,
continue
please,
from here.
please.
Okay.